Quigley, who's going to tell us about Bredon homological stability.
Okay, well, thank you for the invitation to speak, and thanks everyone for coming to the talk. So I'm going to talk about Bredon homological stability, which is some notion of homological stability in equivariant topology. To start, I'm going to remind you a little bit about classical homological stability. And I think I'm less of an expert than probably half the people in the audience. So if there's anything anyone wants to add here, please feel free to do so. So the first homological stability result that I know of is due to Nakaoka in 1960. And Nakaoka showed that the map where I include in the symmetric group on n letters, the symmetric group on n+1 letters, as say the permutations which fix the new letter, this induces an isomorphism on homology. And I could write group homology, but I'm going to go straight to spaces here. So I'm looking at the map from the Deith homology of B sigma n, the classifying space of sigma n, to the Deith homology of B sigma n+1. This map induces an isomorphism for n greater than or equal to 2 times D. So in other words, if I fix a homological degree and I let my spaces go off towards infinity, then I get isomorphisms in homology. And this is an interesting result in its own right, because it tells us something about the homology of symmetric groups. But it's also closely connected to stable homotopy theory via the Barrett-Priddy theorem. So back in 1972, Barrett and Priddy showed that if you take the co-limit of these classifying spaces, perform a plus construction, what that means does not matter at all for the stock, and take the Deith homotopy group of the resulting space, then this is also the Deith stable homotopy group of spheres. So the Deith stable stem. Okay, so Nakaoka's result tells us something interesting about an object related to the stable homotopy groups of spheres. Okay, I'll give you one more example, and this will be like the main example for the talk. This goes back to McDuff and Siegel in the 1970s. So it's 2 separate papers, one by McDuff and one by Siegel. So I'm going to put some weird hypotheses on my manifold, which will make sense later. So let M be the interior of a compact manifold with non-empty boundary. Okay, it takes longer to write than I thought. Okay. So M is, for now, let's just think of it as a manifold. Then we can let Cn of M be the nth unordered configuration space of M. And I'll draw a picture of what a point in that space looks like. So nth unordered configuration space of M. So for instance, let's look at C5 of M. Maybe M is something like a torus. And sitting inside of there, I have a configuration of 5 points. And it's an unordered configuration because I'm not labeling the points. I'm not giving any point priority over the others. Okay, so in this situation, I can define what's called a stabilization map. sigma from the nth configuration space of M to the n plus first configuration space of M as follows. So roughly speaking, what I'm going to do is add a point near the boundary. And this is where that sort of weird hypothesis on M is going to show up. It's so I can define this stabilization map. So the picture here is maybe I've got a configuration of n points in M, and let me make M a little bit simpler now. So I've got some points like this. And let's say my boundary of this bigger manifold, which M is the interior of, is over here. Then what I can do is pick a point in that boundary, take some sort of neighborhood of that point, and choose the way of sort of pushing everything outside of that little area, or sort of stretching things out. And then once I've moved everything out of that little red neighborhood, I can put a new point inside of it. So my new configuration is going to look the same, except that in that little area, I put a new point. Okay, so this is now a configuration in C n plus 1 of M. Okay. And so you might have some objections at this point, like what if I chose a different point in the boundary? Or what if I chose a different way of moving things outside of that little red neighborhood? And those do induce different maps. Well, those are different maps, but they'll induce the same map in homology as long as I stay in the same path component of the boundary. So I'm going to be a little bit lax about that today. In any case, well, okay, let me pause here because these stabilization maps are pretty important in the talk. Are there any questions so far? Okay. If not, so what's the result? Now I have this sequence of configuration spaces and I have ways of mapping between them. So I have the sequence C0 of M, sigma C1 of M, sigma C2 of M, and so on. And I can ask what happens if I take the homology of the spaces in that sequence. And the theorem of McDuff and Siegel is that the induced map in homology, sigma star, from HD of Cn of M to HD of Cn plus 1 of M is an isomorphism for n greater than or equal to 2D. Okay, so we get the same stability range as we had from Nakaoka's result. And in some sense, that's maybe not surprising because if I look at configurations of endpoints inside of R infinity, some infinite dimensional Euclidean space, then this is a model for the classifying space of sigma n. And so if you have some sort of infinite dimensional version of the McDuff-Siegel theorem, you recover Nakaoka's theorem, assuming you can identify the stabilization maps with each other. One other remark that relates this to homotopy theory is that if I instead look at configurations of endpoints inside of, say, an m-dimensional Euclidean space, then this is a model for the nth arity in an En operad. Okay. I think I'm off by something. Maybe it's a quotient of the nth arity. maybe mod sigma n. Yeah. Okay, and so as such, if I look at the homology of these spaces, say with mod p coefficients, then this is closely related to Dyer-Lashoff operations. Okay, so the McDuff-Siegel theorem gives me a sort of qualitative way of understanding these groups, or maybe a quantitative, because it tells me a range where I can compute one to compute a bunch. Okay. So now I want to give an actual definition of homological stability. Maybe I'll just go ahead and do that. So definition, a sequence of spaces x0, x1, x2 exhibits homological stability. If for each d greater than or equal to 0, when I look at the induced map in homology, sigma star from hd of xn to hd of xn plus 1, this map is an iso for n sufficiently large. So in the previous two examples, our sequences were classifying spaces of symmetric groups and configuration spaces. And the n sufficiently large was saying that n was at least 2 times d. One remark I want to make, I think this is like the most classical way of looking at homological stability, but there are many other perspectives on it that are popular nowadays. If the homology of each space, so HDXM, is finitely generated as an abelian group, so I'll say over Z, for all D and N greater than or equal to 0, then the sequence x0, x1 exhibits homological stability if and only if, when I look at the homology of the disjoint union of all of these spaces, this is finitely generated over the ring Z adjoin a single polynomial generator, sigma star. And that sigma star acts on homology by writing it as like a sum of the homology of the spaces and then shifting over using sigma. Okay. And this sort of idea of looking at homological stability, not in terms of sequences of spaces, but in terms of finite generation over some ring, is sometimes also, well, for different rings, this leads to what's called representation stability, very loosely speaking. Okay. At least that's sort of how I understand representation stability, but I'm not an expert, so I could be off. Okay, I want to go on to equivariant stuff now. Are there any questions before I do that?
I just had a comment about your last remark. I guess sort of tautologically, this is really more that the homology is a finitely presented module over that ring. It just, right, because they're for finite generation is that the maps are eventually surjective. Finite presentation would be that they're eventually isomorphisms. But I think for this particular ring, finite generation is the same thing as finite presentation.
Yeah, I think that's right. In this paper with Eva and Chase, we have a little lemma basically checking this remark. And when your underlying ring has some like Noetherian properties, then yeah, you can do it in terms of finite generation. Thanks. Yeah, so let me put in pink. Something like if I had some other R there, then finite presentation would be the correct thing to consider. Thank you.
Sure.
Any other questions or comments? Okay. So I want to go on to the next part, which is Bredon homological stability. So our motivation here is kind of, oops. Well, let me look at these two examples. Up here in Nakaoka's example, there was a homotopical connection, which was understanding the stable homotopy groups of spheres. And down here, there was some connection to operads and power operations. Those are things that I would like to understand in an equivariant context. And so that was sort of the way that we came into wondering about equivariant versions of homological stability. Hopefully at the end, I'll have time to tell you about some other applications that are a little bit less equivariant. Okay, so throughout this discussion, G is going to be a finite group. Let me go ahead and just put abelian to make my life as simple as possible. But a lot of this does go through if I don't impose abelian. So in homological stability, I'm studying homology and I'm studying a sequence of spaces. So let me tell you what the replacements are for both of those. Okay, so classically, I have a sequence of spaces and maps between them, these stabilization maps. In the equivariant world, well, it's not so hard to guess. I'm going to have a sequence of spaces with a group action, so a sequence of G spaces. And I'll give you a concrete example in a sec. And I'm going to ask for G equivariant maps. One, because equivariant maps just seems like the right thing to do, but two, because I need my maps to induce maps in homology. And so what sort of homology are we going to consider? Well, we have a couple of examples, a couple of possibilities, but the replacement we're going to consider is, let me put it in parentheses, it's integer graded Bredon homology. Which I'll denote by homology with a little g in the superscript. Okay. And I guess for the experts, I'm taking integer graded Bredon homology with coefficients in the constant Mackey functor z. A lot of the results I'm going to tell you today hold for other coefficients, but just for simplicity, let's stick with z. And if that doesn't mean anything, it doesn't matter because the entire classical recollection also didn't say what coefficients we were using. Okay, so I don't want to define Bredon homology for you. Instead, I'm going to give you a little slogan, which hopefully tells you everything you need to know about it for this talk. So think of Bredon homology of a G space X as encoding information about the homology of the fixed points of X with respect to every subgroup of G. So think of it as encoding the homology of these fixed points And this is a space, so I just mean literally take the fixed points with respect to the H action. Encoding the homology of XH for all subgroups H and G, plus the relations as H varies. Okay. There's a more careful definition you can give, but then I have to start talking about coefficients. So that's why I want to just stick with this slogan. Any questions or comments so far? Okay. So the main example we're going to consider is the following. So let's say M is a G space. In a second, I'm going to take M to be a G manifold, but for now it's just a G space. If M is a G space, then I can look at unordered configurations of endpoints in M, and this is also a G space. Oops. Okay. So here's a picture. Throughout the talk, my sort of working example is going to be where M is the regular representation of Z mod 2. Which I'll write as 1 is the identity element, gamma is the non-trivial element. And so I'll draw M as like a little complex plane. And the action of gamma flips across the horizontal axis. So if I think of this as being modeled by like the complex numbers, then the action is given by Z goes to Z bar. Okay. So this is my rho. Now, how does Z mod 2 act on configurations? So let's say I have a configuration of 4 points inside of rho. So maybe something like this. Then gamma acts on the ambient space. So it moves all the points inside rho. And in particular, it'll move those labeled points, or the points in my configuration. So it'll flip all of them across the real axis to produce a different configuration of 4 points inside this representation. Okay. So one remark I want to make right away is that these sort of equivariant configuration spaces were already studied by other people. So if V is a G representation, then Cn of V is, okay, now I'm missing a quotient. So it should be the nth arity in what's called an EV operad. So some operad encoding some equivariant multiplication, mod sigma n. And this has been studied by various people. So the first place I saw this was in work of Guillou and May. But there's even older work about equivariant configuration spaces more generally by Rourke and Sanderson. And there's probably many others. Constantinople, Wayner also comes to mind. Okay, so these are sort of interesting spaces, interesting G spaces to play around with. So I have my sequence of spaces, but now I need maps between them. And here I have to be a little careful. So in my setup for this Bredon homology section, I said I want G spaces and equivariant maps between them. So I need equivariant maps. And what that means is that I have to add a fixed point. So let me give you a little illustration. You can tell it's my first time using this iPad because I still haven't figured out how to like copy and paste squares. Okay, so here's this configuration we've already looked at. Let me draw the action going horizontally and the stabilization map going vertically. Okay, so the action, we've already drawn out what it does. It flips everything across the real axis. Now, if I put in a fixed point, I get something like this. And then if I apply the action, well, those blue points move just like usual, and the fixed point will stay where it is, sort of by definition. And you can check, well, I've sort of talked out loud about what happens if you go down and then right, but you could instead go right and down, and you see that the diagram commutes. And just to illustrate what happens if you don't choose a fixed point, if I first go down, and let's say I choose this to be where I add my point, sort of up there on the imaginary axis, then when I apply the action, I'll go down this way. On the other hand, if I apply the action and then add add that point in the same spot, it appears up there. And so the diagram doesn't commute. Okay, so that's why I need to add a fixed point. So with all that said, I now have a sequence of G spaces and equivariant maps, which looks exactly like the sequence before. So C0 of M, C1 of M, so on. And I can ask, does this sequence, does the Bredon homology stabilize after I add enough points? And well, the first sort of surprising thing that we saw in this project is that it doesn't, even in the most simple cases. So let G be just Z mod P, and let M be a G manifold for which our stabilization map, sigma, is defined. So in the language of earlier in the talk, the conditions I want on M are that it's a G manifold, which is, I guess, homeomorphic to the interior of a G manifold with non-empty boundary containing a fixed point. Okay. But it's easier to just say it's a G manifold where I can put in this fixed point near a boundary. Okay, then I can look at the map sigma star in the 0th Bredon homology of Cn of M, Cn plus 1 of M. And this is not going to be surjective for any n greater than or equal to 1. Okay. So we found this a little surprising because, you know, you do this thing when you try to prove things equivariantly, where you just copy the classical situation and hope everything is true. And this is one of those kind of interesting situations where not everything just goes through as it does classically. And the reason is kind of easy to explain. So if we believe our slogan about Bredon homology, then when I look at the Bredon homology of some G space X, this should somehow be related to the homology of the fixed points of X. And the reason this map is not surjective on H naught is because if I look at my configurations of endpoints in M, and then I take the G fixed points, this will contain additional summands as N increases. So it contains new summands as N increases. Okay, and I will draw you a special example which illustrates this point. So let's say G is Z mod 2, and M is the regular representation as usual. All right, so let's look at these fixed points. If I take configurations of 0 points inside of rho, and then take fixed points, well, okay. Configurations of 0 points are pretty boring. It's just an empty configuration. So of course that is fixed under the complex conjugation action. So that's my fixed points. If I look at configurations of 1 point, which are fixed under this Z mod 2 action, well, originally I could put my point anywhere, but now I have to put my point in the fixed points of rho. That is, I have to put my point somewhere on the real axis. Okay. Now let's look at C2 of rho. So now I'm looking for configurations of 2 points, which are fixed under this complex conjugation action. And there's 2 possibilities. So the first thing I can do is just repeat what I did for C1. I can just choose 2 fixed points, something like that. But there's something a little sneaky I can do, which is because these are unordered configurations, if I pick a complex conjugate pair of points, then when I act, it swaps those 2 points, but I get the same configuration. All right, so this is also a fixed point of C2 of rho. And the reason that these maps are not surjective is because this new component is just not even hit under the stabilization map. So sigma is like adding a fixed point here, it's adding a fixed point here. But there's nothing sort of, oops, there's no way of going like this. Okay, so that's the idea of why we don't have a surjection on H naught. Are there any questions at this point? Okay. So hopefully with this picture, it's sort of clear what you should do. Like early on when we said we were going to add a fixed point, if you've done any equivariant homotopy theory, that probably felt like the wrong thing to do. Because in equivariant homotopy theory, there's this slogan that the points are orbits, and adding a fixed point is prioritizing the orbit G mod G, which I'll put down here, over all of the other orbits, in particular over like 3 orbits. And so in order to produce a surjection, or at least have a hope of some form of stability, what we need to do is add stabilization maps, which add other orbit types. So for instance, I can go from C0 to C2 by adding a free Z mod 2 orbit. That's what that these 2 blue dots down here are. Okay, so the fix consider stabilization maps adding other orbit types. Okay, and now you have to do a little bit of work to say precisely what it means to add a free orbit or to add an orbit of the form G mod H. And that translates into a bunch of conditions on the boundary of the manifold that M is the interior of. So let me tell you the theorem. And let's see. Okay, so let G be a finite abelian group. And let M be a nice G manifold. Where nice here means that we can define every possible type of stabilization map. In other words, we can add every orbit type. Then, the Dieth-Bredon homology of the disjoint union over n greater than or equal to 0 of Cn of M is finitely generated over, let's put it down here, the polynomial ring where I adjoin a generator for each conjugacy class of subgroup of G. And conjugacy classes are appearing here because if I mod out by conjugate subgroups, I get the same orbit type. Okay. All right, so that's our homological stability statement, or our Bredon homological stability statement. I want to give one quick remark. There's related work that came out just a few weeks ago of Dan Duggar and Christy Hazel. So what they did was compute the ROG graded Bredon cohomology of ordered configurations of points inside of certain G representations. So they compute this when V contains a regular when V contains at least one trivial representation, and when V also has dimension at least 2. So I mentioned this this connection to equivariant power operations or Dyer-Lashoff operations. And I guess this computation is, I think, a bit closer to actually understanding what those are, at least for certain V. Okay, so that's the theorem. Are there any questions before I talk a little about the proof?
I was wondering, in this picture that you showed to us previously, say if you're considering d equal to 0 still, then if your stabilization map is adding a free orbit each time around, then you seem to be missing the previous orbits. The previous connected components, which had all the points concentrated on the real line.
Right. Yeah, so that's why we end up with this sort of funny statement where we're looking at finite generation over this ring where we consider all possible stabilization maps. So it's not that, it's not that we have sort of sequential stability with respect to one, it's that we have sort of finite generation stability with respect to all. Thanks. Other questions?
Could I ask several things? Like with those maps, those extra sigmas, do you say they have degree appropriate for what the subgroup is. The other ones would have had degree 1, but these, you've got a polynomial ring, but now they've got higher degree, I imagine, right? Yeah. And can I ask with the Duggar and Hazel thing, so they're doing cohomology, and there I think probably you have a different stabilization map which goes in the opposite direction where you forget a point, right? And I wondered if in your situation it might be easier to forget points like that than to adjoin points, which you have to do in an equivariant fashion. Also, I was wondering in their work, what is the group G? Like often in their work, they're considering just the cyclic group of order 2 or cyclic groups. Do you know what their group is?
Sorry, I totally forgot what groups they're considering. I remember talking with Dan and he had some
Well, it doesn't matter.
hypotheses. Yeah. As to your first question, it's something we've sort of wondered about. So I'll explain in a second that our proof is basically by reducing to the classical statement of McDuff and Siegel. So a sort of equivariant to non-equivariant proof. And you could potentially use those techniques if you were instead looking at ordered configurations where you go from n to n-1 to reduce from an equivariant statement to the non-equivariant version proven by Church, I think. But we haven't gone all the way and figured out if it's possible or not. I think one obstruction was, I think Church's result is something that's happening with rational coefficients. Is that right?
Well, I mean, there's Church starts off, and then there's the theory with Allenberg and Farb and so forth, and they're doing. I think like no, it's not rational. I mean, you can. I think you can do it like over. You probably need a field. I can't remember, but I think you can do positive characteristic, for instance. That works.
I see. So that, yeah, so that could be something to explore. I think I got a little thrown off by it by thinking about what the analog of a field or the rationals might be in Bredon cohomology, like for coefficients. I know there is like theories of Mackey fields and stuff, but yeah, I don't know enough about the classical statement to know, but it's a good idea.
Like for the Mackey functors and things, and or the Bredon coefficient systems, I wouldn't. I would think you don't have to look at a field in the category of Mackey functors or something. I would have thought just a coefficient field would be enough, or possibly even over the integers. So I'm not sure. Or local rings. Sorry, go on. I'm sorry. I'm asking to please continue. I'm sorry.
No, it's great. Thank you. Oh, I should ask, am I supposed to end at 3:20 or 3:30?
25 will be great.
Okay, I can do that. Okay. So as I've kind of alluded to, I want to tell you a little bit about the proof. And maybe I'll just give you the faintest idea about future work. And let me say out loud, the future work is work in progress with Eva, Chase, and also Bridget Schreiner, in case I don't get a chance to write her name down. Okay, so what's the proof idea? It's very classical. We use the isotropy separation sequence. So I'll write this as a long exact sequence with a bunch of random looking terms if you haven't seen it before. And then I'll tell you what those are in our case, or at least how they're useful. So I have pi d of proper homotopy orbits, pi d of categorical fixed points, and pi d of geometric fixed points. Okay, and I say this is super classical because like, I think it was used in Carlson's proof of the Siegel conjecture. It was in Hill-Hopkins-Ravenel. So it's a favorite tool in equivariant homotopy theory. Okay, so for us, what is X? X is going to be an equivariant Eilenberg-MacLane spectrum for coefficients in the constant Mackey functor Z, smashed with the disjoint union over N of Cn of M. So by the way, this disjoint union over N of Cn of M, this is just the space of all configurations of any number of points in M. Okay, so what are all these terms? In our case, pi d of xg, this is just the Bredon homology groups that we're trying to compute. So it's the dth Bredon homology of this disjoint union. So this is what we want. What are the other two terms? Well, the left term, this is what's called the proper homotopy orbits. In the case that G is, say, cyclic of prime order, this is just the ordinary homotopy orbits, if that's something you've seen before. The main point of these appearing in our work is that they depend only on homology with respect to proper subgroups. And so inductively, we can reduce to the non-equivariant situation. That is, we reduce to the Macduff-Siegel theorem to understand these proper homotopy orbits. Now, the other piece is geometric fixed points. And in our case, so let me write that out. In our case, these geometric fixed points end up being some huge sum of homologies, of suspensions of the fixed points of our configuration spaces as n varies. So I'm just saying this is sort of the key component that you need to understand these geometric fixed points. And the theorem, which I'm going to be really blasé about, and this is like the main geometric content of the paper, we give a formula for these fixed points of configuration spaces in a G manifold in terms of ordinary configuration spaces. So it ends up being a disjoint union over blah of product over blah of ordinary configurations. So I'll give you an example, but then the point is that these homology groups stabilize again by Macduff-Siegel. Because again, they're just looking at ordinary configuration spaces. Let me try to give an example of this splitting of the fixed points back in this picture. Let me start with C1 of rho G. So what is this really? I'm taking configurations of one fixed point. So that's the same thing as C1 of rho G, which I can think of as, say, like configurations of one point in R. For C2 of rho, I've got configurations of two fixed points. So C2 of R, disjoint union. Well, I have to choose two fixed points, sorry, 2 points which are conjugate to each other. But once I choose one point, the other point is determined by acting by the group. And so I really just have to choose a point in the upper half plane. And up here, I can write whatever I want, but let's say I write C0 of R. And the maps are sort of doing this at the level of what these fixed points are. All right, so the disjoint union is coming from, well, this disjoint union here, and the M prime that appeared was saying sort of like which stratum of M you're taking your configurations in. The product here appears once you have to take configurations of different types of orbits, then you'll be looking at products of configurations. Okay, so that's the main idea. And in the last minute or two, let me just write the summary and the plan for future work. So what was the point of the isotropy separation sequence? So we wanted to understand this Bredon homology, and to do it, we understand this other proper homotopy orbits, which reduces to a non-equivariant stability statement, and geometric fixed points, which by some geometric argument also reduces to non-equivariant stability. So we have stability on the underlying plus stability on the fixed points. And using that long exact sequence, that gives you Bredon stability. So what's the future goal? Maybe I should put a question mark. One thing you could do is look at other sequences of G spaces where you know stability at the underlying level, and you can prove stability at fixed points to produce new Bredon stability results. But one possibility that I think we're all really intrigued by is to take a sequence of G spaces where there's stability at the underlying level. And then instead of looking at the fixed points right away, try to adapt classical proofs of homological stability to prove Bredon stability directly. And so there's all sorts of nice ways of proving stability classically that seem like maybe amenable to the equivariant context. And if you could do this, then you deduce stability on fixed points. And without writing anything out, that could be something which could be interesting to consider. For example, if you look at the fixed points of equivariant classifying spaces, those often split as sums of ordinary classifying spaces of other groups for which stability may not be known. Other possibilities are things like mapping class groups of surfaces or moduli spaces of high dimensional, even dimensional manifolds. If you have things that are even dimensional and you put a little involution on them, then you can sometimes extract something odd dimensional, and stability is less well understood in those cases. So those are sort of the directions we're trying to go. But right now, this is all we know. Okay, I'll stop there. Thanks.
Do you have any questions or comments?
I had two. The first is in this argument, is it, it seems that as you increase the number of points in the configuration, in your example was very illuminating, with the diagram that you drew, but isn't it possible that there are like more components of, it's a disjoint union over a larger collection of configuration spaces as we go from n to n plus one?
Yeah. So maybe one that I didn't draw. So we have C2 up there. I mean, another illuminating thing to draw. I don't know if this is getting at what you're asking, but if I look at, say, C4, then I have my configurations of 4 fixed points. I have my configurations of 2 fixed points and a complex conjugate pair. And I have configurations of 2 complex conjugate pairs. And is your question like, how does this new component get hit, or is it something else?
Yeah, that sounds right.
Okay, yeah, so the idea is this new component is going to be hit by inside of C2 of rho. We had the configurations with 1 complex conjugate pair. And so this is just adding a free orbit.
Oh, I see, I got it, it's in your system, which defines the stabilization, you've got these maps. It's not one
Yep.
map. Yeah.
Yep.
No, that's why the ring has by all of these.
Right.
And can I ask, one other question? So there's another, sort of equivariant version of configuration spaces, which are orbit configuration spaces, where you look at, the nth term is, subsets of order n that miss each other's orbit.
That miss each other's orbits.
If you take the ith point and the jth points, and you take the orbit of the ith points, and the orbit of the jth point, their intersection is empty. So there's a g to the n action on this, which moves each point individually. Is there some chance that these sorts of tools could be used to study the homology of these spaces?
That's a good question. So one thing I can say is that I think these configuration spaces that you're describing are studied in our paper, and also maybe in the work of Rourke and Sanderson. So when we're proving this decomposition of the fixed points into products of whatever, what we're really doing is thinking of like, this is a configuration of 4 fixed points. This is a configuration of 2 fixed points plus 1 free orbit. And over here, this is a configuration of 2 free orbits.
Yeah.
We do, okay. And then as I sort of sketched, you can express this in terms of just ordinary configuration spaces. Like this is just C4 of the fixed points and similar. But this is with respect to just the G action and maybe not a G cross N action. It could be possible to try to use some isotropy separation for the G cross N action, but I'm not sure.
Thank you.
I have a question. So, in your theorem, you have this like niceness condition, like how restrictive do you imagine that would be? Like, you have like, not our examples.
Yeah, that's a good question. So our niceness condition, I'll say out loud, it's that M is the interior of a compact G manifold whose boundary contains every possible orbit type. And so the only examples that sort of naturally arise with those conditions are when M is some sum of copies of a regular representation. I don't know if there's other manifolds which also have this property that people are interested in, but since we were mainly interested in representations anyway, we kind of just left it at that.
Thanks.
But I think it is pretty restrictive.
JD, I have one question. So at some point you do some reduction to the like ordinary stability case. And if I remember correctly, at some point you use this theorem of McDuff and Siegel. I know there is recently this theorem by Kai Philman who proves an equivariant version of this McDuff-Siegel result. And I think this is based on, if I remember the reference correctly, you and Ava posed this question to Kai. If I'm interpreting his writing correctly, could you maybe say something about how you, like, did you want to try to use an equivariant version of this theorem in your story? Like, how did that sort of fit in with this picture?
Yeah, so very early on in this project, that was like our main motivation, was to understand, I guess, the equivariant stable stems via some sort of equivariant homological stability question, or an equivariant homological stability statement. I guess what we learned, by talking with Greenlees, is that it's actually easier. Okay, so maybe I should say the main application we had in mind for this Barrett-Pretty equivalence was understanding like Serre's finiteness theorem in the equivariant stable stems. But it turns out it's like a fairly straightforward consequence of work of Greenlees and May on rational equivariant stable homotopy theory to just deduce that straight up without homological stability.
Okay.
Yeah, but I think you could still take Kaif's result and try to see what our result tells you about the equivariant stable stems, or maybe about equivariant algebraic K theory might be how he's thinking of things. And there, I'm not sure, but it's an interesting question.
Thanks, JD.
Do we have any other questions or comments? Let's thank JD again.
Thanks.